Welcome to the Deep Dive, the place where we take a stack of dense research and distill the absolute best insights just for you.
Got to be here.
Today, we are focusing on a classic, challenging frequency band, 27 megahertz radio.
Ah, yes, CB land.
Exactly. This is the heart of CB radio and also some specialized low-band communications. And honestly, it presents some massive physical constraints, stuff engineers have wrestled with for decades.
Oh, absolutely.
Hmm.
It's a fascinating area because the physics feels so, well, inflexible sometimes.
Hmm.
When you're operating down there, 27 megahertz, the fundamental problem is just the wavelength. It's enormous.
How big are we talking?
About 11.1 meters or roughly 36 feet. And you just can't always install an antenna that long, can you?
No.
Especially not on a vehicle or, in a tight urban spot.
No way. That's the core challenge, right? For peak efficiency, you really need that physical size, but everything modern demands things be smaller, more mobile.
Mm-hmm.
The traditional approach, making the antenna longer if you can, refining the ground plane, maybe installing complex mechanical tuners, it gets you pretty far, but you eventually hit that wall. The size of the wave itself just dictates so much.
And that kind of rigid thinking, that focus only on the physical dimensions, is precisely what this paper by scientific analyst Justin Lake challenges.
Okay, Lake's paper, so what's the new angle here?
Lake proposes a really profound conceptual shift. It's about moving beyond just the purely electrical, the conductive optimization we usually focus on.
And looking where? Instead?
Looking at the magnetic environment surrounding the antenna.
Okay, that's interesting. So the big aha moment here, as Lake sees it, is integrating magnetic field manipulation.
Exactly. Using static fields or dynamic electrical inputs, maybe even advanced magnetic materials.
But not replacing the basic.
No, that's key. It's a complementary path, a way to enhance performance. It's not just about what the antenna is made of, but how you control the invisible forces around it.
So if we can get fine, localized control over that magnetic field, what does that actually buy us?
Well, suddenly you gain new ways to command things like impedance, resonance, even maybe directivity properties that traditionally were dictated almost entirely by the antenna's physical shape and size.
Okay, let's unpack this then. Our mission for this deep dive is to see exactly how these magnetic methods, the ones Lake proposes, can potentially provide maybe a dramatic performance boost.
Right, we're looking at improving efficiency, maybe enabling real-time tuning.
And ultimately, maybe extending the practical, reliable range of a standard, legally limited 4-watt transmitter. Because that's the reality for most users, isn't it? 4 watts.
It is. This is really about making every single milliwatt count, getting the absolute most out of that legal limit.
All right, so to really grasp Lake's solution, we probably need to revisit the fundamentals. The electromagnetic wave itself at 27 megahertz. We know it's this wave of energy oscillating between two components.
That's right. You've got the electric field, the E field. That's the one we usually think about with antenna length and voltage,
Mm-hmm.
And then you have the magnetic field, the B field, which is perpendicular to it. As the wave travels through space, energy is constantly converting between these two fields. That's what radiation is.
And in free space, they're linked, right? The strength of the B field is related to the E field strength by the speed of light, wasn't it?
Exactly. B is approximately E divided by C, the speed of light. Now, what's absolutely critical here, and this is what really opens the door for Lake's innovation, is the sheer magnitude of that relationship.
How so?
Because the speed of light is so incredibly fast. It's a truly massive number, 3 times 10 to the 8 meters per second. The magnetic component, the B field that's generated by the radio signal itself, from those 4 watts.
Yeah.
It's actually incredibly weak compared to the E field.
Okay, wait. If the radio wave's own B field is inherently weak, why are we bothering trying to manipulate it? Doesn't that seem a bit counterintuitive? Like trying to steer a battleship by, I don't know, blowing on its sail?
That's the perfect question. And it gets right to the core insight Lake identifies in the paper. Because the intrinsic B field, the one made by our 4 watts of RF energy, is so weak, it actually means that the external magnetic fields an engineer can practically apply, well, they're strong enough to meaningfully influence the antenna's performance.
Ah, I see. So the weakness of the wave's own magnetic field is actually the opportunity here.
Precisely. We can use comparatively small, manageable external magnetic forces to dramatically alter the magnetic environment right near the antenna where it counts.
That totally reframes the problem. We're not trying to overpower the wave's own field. We're using external forces to gently, or maybe not so gently, nudge how the antenna system behaves magnetically.
Exactly, influencing the local conditions.
Okay, so let's look at the core interaction principles Lake identifies. First up is this idea of magnetic biasing. What's that about?
Magnetic biasing is all about deliberately altering a material property called permeability, usually written as BU.
Permeability. That rings a bell. It's about how well a material supports a magnetic field, right?
You got it. How well it can concentrate or channel magnetic flux lines. Now, if we use specific magnetic materials in the antenna system, maybe in an inductor coil, or as part of the feed line connection, and then we apply an external static magnetic field to those materials.
Like from a permanent magnet or an electromagnet running on DC?
Either one. The point is, applying that steady external field changes the permeability of the magnetic material almost instantly.
Okay, so the material property changes. How does that translate into antenna performance? What does it do?
It fundamentally changes how that specific component interacts with the radio frequency signal passing through it. It effectively changes the material's characteristics on the fly.
Ah, okay.
And this is the foundation for things like dynamic real-time tuning, which I'm sure we'll get into more detail on later.
Makes sense. Okay, next principle, ferrite loading. Now, ferrite, that's something many listeners might recognize, those clamp-on beads for cables.
Right? Often used as chokes to suppress unwanted noise, especially at higher frequencies. But here, Lake is talking about using ferrite much more proactively as part of the tuning system itself.
How does that work at 27 megahertz?
It involves using high permeability magnetic ceramic materials, ferrites, that are specifically chosen or designed to interact effectively with the magnetic component of the RF energy at this frequency, at 27 megahertz.
So you need the right kind of ferrite.
Absolutely critical. You place a ferrite core or sleeve near a conductor in the antenna system, like around the base of a vertical antenna or the feed point. What happens is the ferrite interacts with the magnetic field generated by the RF current.
And that does what?
It effectively increases the inductance in that part of the circuit path.
Okay, increase inductance, and that affects the tuning.
Directly.
Hmm.
When you increase the inductance, you directly modify the resonant frequency of the antenna system. It essentially makes the antenna appear electrically longer than it physically is.
Without actually adding metal.
Exactly. You're using the magnetic properties of the ferrite to achieve electrical length.
This sounds really crucial for those miniaturization efforts we talked about. If I can add effective inductance using a lump of ferrite, maybe I can use a physically shorter whip antenna and still make it resonant on that long 11.1 meter wavelength.
That's precisely the goal. It's like using magnetics to cheat the physical length requirement, allowing for smaller, more practical antennas.
Very cool. Okay, third principle, near field shaping. This one sounds a bit more exotic, controlling the energy right at the source before it even properly radiates.
Yeah, this is where it gets really interesting. Think of it like trying to create a magnetic lens for the energy right as it's leaving the antenna structure.
How would you do that?
By introducing carefully controlled high local B fields extremely close to the antenna elements themselves. These intense local fields can fundamentally alter the way energy couples from the antenna structure into the surrounding space.
And what are the main goals of doing that? Better efficiency?
That's one primary goal, yes, to improve the amount of energy that actually successfully launches into the air as radiation. But another very important goal, according to Lake's analysis, is potentially reducing unwanted side lobe radiation.
Ah, side lobes. So that's power essentially getting wasted, right? Shooting off in directions we don't want, maybe even reflecting back towards the radio.
Exactly. Parasitic radiation. It reduces the power going into your main desired direction, and it can sometimes cause interference. If we can use near-field magnetic shaping to kind of guide more energy into that main beam and suppress those unwanted side lobes.
Then our 4 watts suddenly performs better. It behaved like maybe 5 or 6 watts from a less efficient, more leaky antenna.
That's the idea, making the radiation pattern cleaner and more focused using magnetic influence close in.
Okay, and the final principle Lake mentions is loss control. This one feels a bit counterintuitive to me. Don't magnetic materials, especially ferrites, often introduce loss into RF systems if you're not careful? How can adding them help control loss?
You're absolutely right to be cautious there. Poorly chosen magnetic materials, or materials used at the wrong frequency, can be disastrous loss generators. They just turn RF into heat.
So what's Lake's angle here?
Lake argues for controlled damping using magnetic induction. It's about using the lossy properties of certain magnetic materials strategically. While minimizing overall loss is usually the goal, sometimes a specific, targeted loss can be beneficial.
How so? What kind of loss would you want?
Think about harmonic resonances. Your transmitter is putting out 27 millihertz, but maybe the antenna system also has some unwanted resonance at, say, 54 millihertz or 81 megahertz multiples of the main frequency.
Ah, harmonics. They can cause interference and waste power.
Exactly. So by introducing a magnetic material that has specific frequency-dependent loss characteristics, meaning it's lossy at 54 megahertz, but maybe not so lossy at 27 megahertz, you can selectively suppress that unwanted harmonic energy.
So you're introducing a carefully calibrated surgical loss at the wrong frequencies to improve the clarity and efficiency of the right frequency signal.
Precisely. It's about using magnetic loss as a tool to clean up the signal spectrum and damp out parasitic modes.
Okay, that theoretical foundation is really helpful, understanding why magnetics might work. Now let's get into the engineering specifics outlined in Lake's paper, the how-to. This is where it gets really interesting for me. How does actually putting specific ferrite materials near an antenna change the physics in a way that gives, real quantifiable benefits to the average CB operator?
Right. Moving from theory to practice. As Lake details, it really comes down to that property we mentioned, the frequency-dependent permeability, the route of the ferrite material itself.
Meaning not all ferrites are created equal.
Not at all. Ferrites are basically ceramics, iron oxide mixed with other metals like manganese, zinc, nickel. Their exact composition dictates which frequency range they work best in, where they have high permeability and relatively low loss. For 27 millihertz, you need a material specifically optimized for that lower HF range, often called a high permeability mix suitable for HF frequencies. Okay, so you get the right mix, you put it near the antenna, it interacts with the antenna's near-field B field. What are the tangible effects we'd actually see? What changes on, say, an SWR meter or in performance?
Lake highlights a few key effects. One, as we discussed, it acts as that electrical shortcut. It can slightly shorten the physical antenna length needed to achieve resonance at 27 millihertz.
Handy for making antennas smaller.
Definitely. Two, and this is absolutely crucial for that 4-watt challenge we keep mentioning, it can dramatically reduce the standing wave ratio, the SWR.
Ah, okay, now you're talking. A lower SWR is like the holy grail for radio operators. Less reflected power, more power going out. How exactly does the ferrite achieve that SWR reduction?
Great question. Remember, SWR is basically a measure of the impedance mismatch between the transmitter's output, usually 50 ohms, and whatever impedance the antenna system presents at the feed point. A poorly tuned or physically compromised antenna might present, 10 ohms or maybe 300 ohms, a big mismatch.
Right, leading to high SWR. The ferrite helps by introducing a controlled amount of complex impedance right near the feed point. This impedance has both resistive and, importantly, reactive, specifically inductive components.
Okay.
This added complex impedance acts like a sort of built-in virtual matching network. It helps transform the antenna's natural impedance closer to that ideal 50 ohms the radio wants to see. Lake's simulations showed this effect can be quite substantial, leading to significant SWR drops.
My sense, it's like adding the right component right where the mismatch occurs. And I think you mentioned a third effect earlier, bandwidth.
Yes, improved bandwidth. While the CB band itself is relatively narrow, being able to operate effectively across all 40 channels, from roughly 26.965 MHz up to 27.405 MHz without major SWR spikes is really important for usability.
Sure, you don't want to have to retune constantly just to change channels.
Exactly. By introducing the ferrite's magnetic structure near the feed point, you often broaden the range of frequencies over which the antenna maintains an acceptable match, say below 1.5.1 or 2.1 SWR. It makes the whole system much more robust and forgiving across the band.
The implementation details seem critical here, though. Lake really stresses you can't just grab any old ferrite noise, choke off a USB cable, and slap it on your CB antenna.
Oh, absolutely not. That would likely be disastrous. The ferrite cores or sleeves must be placed strategically, usually right around the feed line at the antenna base or feed point is most effective. And crucially, the magnetic composition must be perfectly tailored for optimal performance, specifically around 27 megahertz.
What happens if you use the wrong type? Say, a ferrite meant for suppressing noise up in the VHF or UHF range.
If you use a ferrite mix designed for, say, gigahertz noise suppression, down at 27 megahertz, it'll likely exhibit very high magnetic loss. Instead of providing useful inductance, it will just act like a resistor. It'll get hot.
Burning up your precious 4 watts as heat instead of radiating it.
Precisely. It becomes a dummy load. The material science has to be frequency-specific to ensure the ferrite primarily converts the magnetic energy into useful inductive reactance, minimizing the wasteful heat loss.
Okay, that clarifies the passive approach with ferrets. But Lake's paper also pushes into active control. Let's explore this idea of real-time tuning via magnetic biasing. This sounds like introducing dynamic adjustments.
It is. This is where we really capitalize on that principle we discussed earlier, being able to change a material's permeability on demand.
How's it implemented?
The method involves applying a controllable static DC magnetic field to inductor coils that are already part of the antenna matching network. These could be toroidal inductors or maybe solenoid coils used for antenna loading.
So you have your normal RF matching coil, and then you apply a separate DC magnetic field to it, maybe from a small electromagnet nearby.
Exactly. You're using a separate, relatively low-power DC circuit to influence a component that's handling the high-frequency RF power.
What's the effect? What does that DC bias field do to the RF inductor?
It changes the operating point of the magnetic core material within that inductor. This alters its effective permeability, which in turn shifts the inductance value of a coil almost instantly.
Ah, so you can change the inductance electronically without physically tapping the coil or adjusting a capacitor?
Precisely. And this is huge because it allows the operator, or maybe even better, an automated microcontroller system, to continuously tune the antenna's resonant frequency without physically moving anything.
I can see the application immediately. Imagine you're driving your truck, you go under a big steel overpass, or maybe you drive into a heavy downpour.
Or even just people moving around near a portable antenna. All things that can instantly detune a finely tuned rigid antenna system, the impedance changes.
Right. And traditionally, you'd see your SWR shoot up, your signal would drop. You might have to stop, physically adjust the antenna wib, or fiddle with a manual tuner knob inside the cab.
Exactly. But Lake's proposed method allows the system to potentially compensate for that environmental detuning almost instantly. If the resonance shifts slightly off frequency, the control circuit adjusts the DC bias current, which changes the inductance, pulling the resonance right back where it needs to be.
So the antenna stays resonant, SWR stays low, and your 4 watts keeps radiating efficiently. That provides a level of consistency that's really hard to achieve otherwise, especially in mobile setups.
It's a major potential advantage. Moving from mechanical or passive tuning to potentially electronic magnetic tuning offers much faster and more precise adaptation.
Okay, let's talk about the next method. Near-field magnetic coupling. This one sounded a bit more experimental, maybe involving influencing the actual radiating element itself.
It is presented as perhaps a more advanced or experimental technique in the paper, yes. This involves applying external AC or DC magnetic fields very close to the main radiating elements of the antenna, particularly if those elements are already ferrite-loaded.
So not just influencing a matching coil, but the antenna wire or tube itself.
Potentially, or components very close to it. The idea is that the external field influences the instantaneous energy transfer process right where the RF is turning into radiation.
Lake notes the effects might be subtle but potentially powerful. Things like modifying the antenna impedance slightly, maybe getting a small extra boost in radiated power efficiency. But the effect he seemed to emphasize most was suppressing parasitic modes. Can you unpack that?
Sure. Parasitic modes are essentially rogue resonance points or unwanted current distributions on the antenna structure itself, or even on the feed line. They're like little unintended antennas coupled to your main one.
And they're bad because?
They're terrible power sinks. They steal energy that should be going into your desired signal at 27 millihertz. They can generate noise, distort the signal's frequency purity, and generally mess up the radiation pattern.
Okay, so how does applying a local magnetic field help suppress them?
By applying a carefully shaped magnetic field in the right spot, you might be able to introduce controlled damping or alter the current flow in a way that specifically discourages those rogue current loops from forming or resonating. It's like magnetically massaging the energy flow near the antenna to push all the power solely into the desired transmission mode and kill off the parasitic ones.
Fascinating. Almost like noise canceling, but for RF currents on the antenna itself. Now, this next section in Lake's paper really steps into the laboratory of the future, metamaterials and magnetic nanocomposites. This sounds like hardcore material science applied directly to antenna design.
It absolutely is. This is Lake's forward-looking vision, moving beyond just placing an off-the-shelf ferrite sleeve near an antenna. Here we're talking about something much more integrated,
Like what?
like embedding specifically engineered magnetic nanoparticles directly into the materials used to build the antenna or its housing, into the plastic substrates, the protective coatings, the composite structural materials.
So the magnetic properties are baked right into the antenna's fabric, so to speak.
Exactly. And the huge significance, as you hinted at before, is the potential to achieve truly engineered permeability and other magnetic properties. We aren't just accepting the characteristics of naturally occurring ferrite mixes. We could potentially design materials almost atom by atom to interact with 27 MHz radiation in precisely the way we want.
And this changes everything you mentioned, especially for small devices.
That's the dream. If you can control the local magnetic environment with that level of precision, right within the antenna structure, you could potentially achieve things like highly frequency selective enhancement, making the antenna incredibly efficient only at 27 MHz and rejecting other frequencies. And crucially, you might finally crack that fundamental size constraint.
Because the engineered material provides the necessary electrical length or impedance matching internally.
Precisely. This kind of technology holds the promise for extreme miniaturization while hopefully maintaining decent performance. Imagine a truly effective, high-performing 27 MHz antenna embedded invisibly within the case of a handheld CB radio, where currently you need that long, awkward whip antenna to get any useful range at all.
That really would be the holy grail for portable CB use, wouldn't it? Making it genuinely pocketable and still effective.
It's the long-term potential that technologies like magnetic nanocomposites offer, according to Lake's outlook.
Okay, this theory and the vision for the future are really compelling. But ideas are one thing. Lake backs this up with rigorous modeling, right? We need to look at the data. What did the simulations actually show? Let's start with the ferrite performance.
Right. Lake didn't just theorize. The paper includes results from standard, well-validated antenna modeling software tools like NEC, Numerical Electromagnetics Code, and its easier-to-use variant EasyNAs. These are the industry-standard tools for simulating how antennas radiate.
And what did those models predict for fair loading on a typical CB antenna?
The simulations, modeling things like placing optimized ferrite sleeves around a standard quarter-wave 27 MHz vertical antenna, showed they could reduce the SWR by a really tangible amount, something like 15 to 25% across the entire CB frequency band, channels 140.
Okay, let's translate that 15-25% SWR drop for the listener. That's not trivial. Going from, say, an SWR of 2.0.1, which isn't terrible but reflects about 11% of your power, down to maybe 1.5.1, which reflects only 4%. That's a significant chunk of your precious 4 watts suddenly making it out of the antenna instead of bouncing back to the transmitter.
Exactly. It means significantly less power is wasted as reflection. And the beauty, as Lake points out, is that this gain comes purely from manipulating the magnetic environment near the feed point, not from building a physically larger or more complex antenna structure. It represents refined efficiency.
Okay, so the passive ferrite approach shows promise in simulation. What about the active control aspect, the magnetic biasing for real-time tuning? Lake used different software here you mentioned, SPICE models. Why the switch?
That's a great observation, and it highlights the kind of cross-disciplinary thinking needed here. NEC and EasyNAC are fantastic for simulating the antenna's radiation patterns and impedance in free space. But SPICE-IE, that stands for Simulation Program with Integrated Circuit Emphasis, is designed specifically for simulating electronic circuit behavior.
Ah, okay.
Since magnetic biasing works by influencing the inductor coils within the antenna matching network, which is essentially an electrical circuit, SPICE-E is the much better tool to accurately model how applying that external DC magnetic field affects the performance of that LC inductor capacitor matching circuit.
Makes sense. Use the right tool for the job. So what did the SPICE circuit simulations show in terms of dynamic tuning capability? How much could they actually shift the resonance?
The models described in the paper indicated that by applying a reasonably manageable external DC magnetic field to the matching coil's core, they could achieve resonance shifts of roughly plus or minus 50 to 100 kilohertz.
50 to 100 kilohertz. That might not sound like a huge frequency shift in the grand scheme of things, but in a narrowband system like CB radio, where the channels themselves are only 10 kilohertz apart.
It's actually a massive amount of control. That range, 50 to 100 kilohertz, is more than sufficient for precise fine-tuning to counteract common environmental detuning factors.
So if your antenna's resonance gets pushed off frequency by, say, 75 kilohertz because you parked near a metal building, this system could theoretically apply the right bias field to shift the resonance right back onto your target frequency, like 27.185 millihertz for channel 19.
That's exactly the potential. It means the system could automatically maintain that perfect SWR and peak efficiency, even if external conditions are trying to mess it up. As we said, that consistency can often be more valuable in the real world than just achieving a perfect tune under ideal static conditions. Magnetic biasing offers that dynamic consistency.
Okay, finally, let's look at the simulation results for the really futuristic stuff, the nanocomposite shaping. Lake used yet another tool here, finite element method, or FEM modeling. Why FEM for this one?
FEM modeling is the tool of choice when you need to get really granular and analyze the complex interactions within a material itself. It's ideal for understanding how electromagnetic fields behave right at the boundaries and within the bulk of composite materials, especially when you have things like magnetic nanoparticles embedded in a non-magnetic substrate. You need that higher resolution physical model to accurately predict the near-field flux density changes.
Right, because here you're not just modeling a simple wire antenna or a circuit, but the fields inside this custom engineered material.
Exactly. And the FEM modeling Lake references demonstrated something quite promising, that these engineered magnetic coatings or substrates could significantly increase the near-field magnetic flux density right near the antenna surface.
Concentrating the energy more effectively, like that magnetic lens idea.
That seems to be the interpretation, yes.
Yeah.
Getting the energy coupled more efficiently right at the source. But crucially, the models also show that this could be done while ensuring the far-field radiation pattern, the signal that actually travels out, remains stable and predictable.
That's a critical point. You don't want to gain near-field efficiency at the cost of screwing up your main signal beam.
Absolutely.
Yeah.
You want the benefit of that super efficient energy coupling close in the focusing lens effect without distorting the signal once it leaves the immediate vicinity of the antenna, preserving the desired directionality and pattern shape. The FEM results suggested this might be achievable.
This all sounds incredibly promising based on the modeling. But Lake's paper is also realistic, isn't it? It outlines several practical limitations and trade-offs that need serious consideration before we see this widely implemented.
Oh yes, absolutely. This isn't magic. There are real engineering challenges. The first big hurdle mentioned is the required field strength.
For the biasing and shaping.
Yes. To meaningfully influence these high permeability materials and achieve those useful tuning shifts of 5100 kilohertz, or to significantly shape the near field, the external magnetic fields you need to apply locally have to be quite strong. The paper mentions figures typically in the range of tens to hundreds of millitesla.
Hundreds of millitesla. That's a pretty powerful magnetic field to generate and maintain consistently, especially in a compact or mobile environment like a vehicle. That requires significant current for an electromagnet or a strong permanent magnet.
It does. It's not insurmountable, but it's a definite design challenge in terms of power consumption, heat dissipation if using electromagnets, and physical packaging. And if you miscalculate or your control system malfunctions and you apply too strong a field,
Then you run into other problems.
you certainly can. The paper points out the immediate risk of inducing unwanted eddy currents, especially if you're using AC fields for shaping, or if the DC bias field interacts poorly with the RF signal itself.
Eddy currents. Those are basically little swirling currents induced in nearby conductive materials by the changing magnetic field.
Exactly. And they're bad because they act like resistors. They just dissipate energy as heat. So if your strong magnetic control field starts inducing significant eddy currents in the antenna base, the mounting hardware, or even the matching network wiring itself.
You could end up losing more power to heat than you gain from the magnetic tuning effect.
Precisely. It's a delicate balancing act. You need the field strong enough to influence the magnetic material, but not so strong or poorly controlled that it causes excessive eddy current losses in all the surrounding metal bits. Careful design and material selection are key.
And beyond just efficiency losses, we absolutely have to consider safety and potential interference when we're talking about generating strong magnetic fields.
That's a huge practical consideration, and Lake acknowledges it. Blasting strong magnetic fields, even locally, requires very careful thought about the immediate environment. What other electronics are nearby? Is the operator exposed?
Right. Could it interfere with the vehicle's engine control unit, GPS navigation, other radios, or sensitive sensors?
Exactly. The risk of unintended electromagnetic interference, or EMI, is very real when you start actively manipulating strong magnetic fields. Careful shielding might become necessary to contain the field and prevent it from causing crosstalk or coupling with other sensitive systems. Safety standards regarding human exposure to strong static or dynamic magnetic fields also need to be considered.
So it sounds like the ultimate conclusion Lake draws here, and something really important for our listeners to grasp, is that these magnetic enhancement techniques are not a magic bullet replacement for good old-fashioned antenna basics.
Absolutely not. You still need a fundamentally sound antenna system to start with. You still need a good electrical connection, a decent ground plane, especially for verticals, reasonable height above ground, and low-loss feed line. Those things don't go away.
It's more like a powerful complementary tool.
That's the perfect way to put it. Magnetic enhancement takes an already well-designed system, one that obeys the classical laws of antenna theory, and gives you an extra layer of control. It allows you to achieve a degree of fine-tuning, dynamic consistency, and potentially efficiency refinement that purely mechanical or passive electrical systems often struggle to provide, especially under changing real-world conditions.
All right, this is the moment where we really need to bring all these fascinating magnetic efficiency gains back down to earth, back to the practical reality for most CB users.
Right. We've talked about lowering SWR, maintaining resonance, maybe shaping the field, but how does that translate into actual performance when you're strictly limited by law?
Exactly. The context is that strict regulatory limit, which is just 4 watts peak envelope power, or PEEP, for citizen band use here in the US. You can't legally just crank up the power.
So if we connect this back to the bigger picture, what does minimizing SWR by, say, 25% using ferrite loading, or maintaining perfect resonance with 75 kilohertz precision using magnetic biasing, what does that really mean for a typical user who can never, ever exceed 4 watts input power?
Well, I guess those things to remember, as Lake implicitly acknowledges, is that you're likely losing some power before it even attempts to leave the antenna.
True. Even with a perfect radio putting out exactly 4.0 watts PEP.
Your feed line, the coaxial cable running to the antenna, has loss. And even with good tuning, there's usually some small residual SWR loss. Lake's paper seems to assume a typical system might already lose maybe 0.5 to 1 decibel dB just in the feed line and mismatch.
And 1 dB loss means about 20% of your power is gone. So your 4 watts at the radio might only be 3.2 watts actually arriving at the antenna feed point. Every little bit of efficiency gain at the antenna becomes even more critical.
Okay, but despite that low power, 27 megahertz still has some inherent advantages for communication, right? It's related to the physics of that long wavelength.
Absolutely.
Yeah.
We have to look at something called free space path loss, or FSPL. Basically, how much the signal weakens just by traveling through empty space. Because the wavelength at 27 megahertz is so long, 11.1 meters, the signal strength drops off relatively slowly with distance compared to much higher frequencies, like the microwave bands used for Wi-Fi or modern cellular phones.
That longer wave is just more resilient somehow. It doesn't dissipate its energy quite as quickly over distance.
In simple terms, yes. Lower frequencies generally suffer less path loss for a given distance, and this ties directly into the dominant way signals travel at this frequency for local communication.
Which is ground wave propagation, right?
Exactly. Ground wave is the real bread and butter for reliable local 27 megahertz communication. We're talking typical distances of, say, less than 10 or 15 miles, maybe 16 to 24 kilometers.
And ground wave is special because it doesn't just travel line of sight.
Correct. Crucially, ground wave signals tend to follow the curvature of the Earth, at least to some extent. They can diffract or bend over hills and obstacles much better than higher frequency signals can. This ability to hug the terrain is why CB radio can be surprisingly effective for reliable short to medium range comms, even in areas that aren't perfectly flat.
Okay, so ground wave is the reliable workhorse. But then there's the exciting, but maybe less predictable phenomenon, sky wave, or ionospheric skip.
Ah, yes, Skip. This is what gets people excited. It happens when your 27 megahertz signal, instead of just traveling along the ground, shoots up at an angle and hits the ionosphere, that electrically charged layer high up in the Earth's atmosphere.
And bounces back down.
Under the right conditions, yes. The ionosphere can act like a mirror and reflect the signal back down to Earth hundreds, sometimes even thousands of miles away. This is the scenario where your little 4-watt CB signal can suddenly, unexpectedly, be heard halfway across the country or even internationally.
But it's not something you can rely on day to day.
Absolutely not. Skip conditions are highly dependent on factors like the 11-year solar cycle, the time of day, often better near dawn and dusk, the season, and even space weather events like solar flares. It's fascinating when it happens, and it shows the potential reach of low power on this band, but you certainly can't bank on it for essential local communication.
This really drives home Lake's core point about antenna efficiency, doesn't it? If you've only got 4 watts to play with, and ground wave is your main reliable mode, making sure as much of that 4 watts actually gets radiated effectively is paramount.
It's everything. Think about the contrast. If you use a really inefficient antenna, maybe one of those tiny, heavily loaded magnet mount antennas stuck on a car roof with a poor ground connection, you might literally only be radiating 10% or 20% of your 4 watts.
So maybe only half a watt actually gets into the air. The rest is just heating up the loading coil or the coax shield.
Exactly. Whereas a well-designed, resonant, properly installed system, like a full-size quarter-wave vertical antenna with a good ground plane made of several radials, can potentially radiate over 90% of the power that reaches its feed point. Huge difference in effective signal strength. Massive. And the magnetic enhancement techniques Lake proposes are essentially aiming to do two things. First, help even physically compromised antennas get closer to that high efficiency mark by improving the match and potentially reducing losses. And second, help maintain that peak efficiency even when environmental conditions change, using things like the magnetic biasing for real-time tuning. It's all about maximizing that radiated power within the 4-watt legal envelope.
We also can't ignore the impact of the immediate terrain, even with a perfectly optimized antenna. Lake's paper doesn't claim magnetic tuning can make signals go through mountains, right?
No, physics still applies. Urban clutter-dense buildings made of steel and concrete is a massive attenuator for RF signals. Dense forests, significant hills, mountainous terrain, these things will always reduce range.
Conversely, open flat terrain, especially over ground that conducts electricity well, like moist soil or salt water.
That significantly improves range because the ground wave can propagate much more efficiently with fewer obstructions and better reflection off the ground itself. The benefit of the magnetic tuning techniques in these scenarios is that while they can't remove a building or flatten a hill, they ensure that the maximum possible power is being radiated from the antenna in the first place, giving the signal the absolute best chance to overcome the path losses it will inevitably encounter.
Okay, so let's try and tie all this together for the listener. We've talked theory, methods, simulations, and propagation. Now, based on Lake's analysis of optimization potential, what are the sort of realistic, reliable communication ranges someone could expect with a truly optimized, legal 4-watt CB system? One that maybe incorporates some of these magnetic precision techniques.
Right, putting some numbers on it, while keeping in mind these are always estimates. Lake's work implies that by maximizing efficiency, you can push the reliable ground wave range. He seems to break down the estimated reliable ranges based on the typical operating environment, assuming you've achieved peak optimization.
So starting with the toughest environment.
Yeah.
Dense urban areas, lots of buildings, metal, electrical noise.
Yeah, in heavy urban clutter. Even with a perfectly tuned 4-watt system, the range is typically very constrained by signal absorption and reflection. You're probably looking at something like 1 to 5 miles, maybe 1.5 to 8 kilometers for truly reliable communication. In this environment, getting your antenna placement absolutely right, as high and clear as possible, is critical, but even the best tuning struggles against just massive RF absorption by buildings.
Okay, what about moving out to more typical suburban areas? Less density, maybe more houses than skyscrapers, some trees.
Here, things improve significantly. With fewer massive obstructions, you start to see the benefits of antenna height and efficiency more clearly. Reliable range often extends out to maybe 5 to 10 miles, roughly 8 to 16 kilometers. This is where getting your antenna masked up even just another 10 or 20 feet can make a really noticeable difference.
And then the ideal scenario for ground wave, open flat terrain, maybe rural areas over farmland or near the coast.
This is where you really maximize that ground wave potential. In open flat terrain, especially with good ground conductivity, a well-optimized 4-watt system can achieve reliable ranges of 10 to 15 miles, sometimes even a bit more, so roughly 16 to 24 kilometers. This is the kind of environment where the consistency provided by something like magnetic biasing, maintaining that perfect SWR and resonance despite minor environmental shifts, really shines. It helps ensure the signal remains robust over that entire potential distance.
And just for completeness, that fun outlier, favorable ionospheric skip conditions.
Right, the unpredictable bonus round. When skip conditions are good, Lake's underlying physics confirms that even 4 watts can go surprisingly far. Those rare, high-impact ranges could potentially push 50 to 200 miles, maybe even further on exceptional days. That's 80 up to 320 kilometers or more. But again, totally unreliable for planning purposes.
This discussion about range really leads to a critical takeaway from Lake's perspective, doesn't it? It's about the relationship between optimizing efficiency versus just trying to increase power.
Absolutely.
Yeah.
Lake's work implicitly reinforces a fundamental rule of thumb in radio physics. For line-of-sight paths, doubling your transmitter power does not double your range. Because of the way radio waves spread out, the inverse square law, doubling your power only increases your theoretical maximum range by the square root of 2.
Which is only about 1.4 times the range. So going from 4 watts to 8 watts wouldn't get you twice as far, only about 40% further, even theoretically.
Exactly. And this really highlights why focusing on efficiency, especially when you're legally capped at 4 watts like in CB radio, is so incredibly vital. You can't legally jump to 8 watts or 16 watts. Trying to chase raw power is not only illegal, but also yields diminishing returns in terms of range increase.
Whereas improving your antenna system's efficiency, that's where the real gains are.
That's the most powerful move you can make within the rules. If you use techniques like those Lake proposes, maybe ferrite loading or magnetic biasing, to reduce your SWR from, say, a mediocre 2.5.1 down to an excellent 1.1.1, the resulting increase in your effective radiated power, ERP, can often provide a much more significant boost to your actual communication range than the theoretical gain you'd get from illegally doubling your transmitter power. You're maximizing the output of the transmitter you already have and are legally allowed to use.
So Lake effectively provides a kind of final optimization checklist, combining both classical best practices and these newer magnetic concepts for any user aiming to squeeze the absolute maximum performance out of that legal 4-watt limit.
Yeah, it boils down to a few key areas. First, and perhaps most obviously impacted by Lake's work, tuning. You absolutely must achieve a low SWR, ideally below 1.5.1, and ensure your antenna is truly resonant right on your desired operating frequency, like 27.185 MHz for channel 19. The magnetic biasing methods offer a potential way to maintain this precision dynamically, constantly fighting environmental drift.
Second, the classic advice: height is king.
Always. Increasing antenna height, especially getting the radiating part significantly above surrounding obstructions, ideally in increments related to the wavelength, like a quarter wavelength or more above ground or obstructions, dramatically improves both your ground wave reach and your line of sight distance. No amount of tuning can make up for an antenna buried down low.
Third, particularly for vertical antennas, which are common in mobile setups, don't skimp on the ground plane.
Critically important. Lake's principles assume a decent starting point. For a typical quarter wave vertical, having an effective ground plane, whether it's the metal vehicle body or for base stations a set of 8, 16, or even more radial wires spread out, ideally each about a quarter wavelength long, is absolutely essential. The ground plane provides the other half of the antenna and helps convert the electrical current into effective radiation instead of just wasting energy heating the ground or the feedline braid.
And fourth, another classic but crucial point: minimize feedline loss.
Yes. Use the best quality, lowest loss coaxial cable you can reasonably afford and justify for your setup, especially for longer runs. And keep those cable runs as short as practically possible. It makes no sense to gain, say, 0.8 dBs of efficiency at the antenna through clever magnetic tuning if you then immediately lose 1 dB or more in a long run of cheap, lossy coax cable. The entire system, from the radio's output jack to the tip of the antenna, has to be treated as a chain, and every link needs to be optimized. #outro.
Well, this has been a fascinating deep dive into scientific analyst Justin Lake's paper. It really confirms that even a band like 27 MHz radio, despite those significant low power constraints and the tyranny of that huge 11.1 meter wavelength, is still very much a frontier for innovation.
Absolutely. I think Lake's core conclusion is genuinely transformative for how we might think about antennas in this space. The idea that by actively or passively integrating magnetic fields and advanced magnetic materials, we gain this precise control over resonance, SWR, and even near-field energy shaping. It's powerful.
It offers a way to get reliable, fine-tuned performance adjustments without necessarily needing complex mechanical parts or having to physically alter the antenna structure itself. That seems like a big step forward.
And we saw that the future potential, especially with things like engineered magnetic nanocomposites, holds the promise of finally cracking that miniaturization problem while hopefully maintaining high performance. That's a crucial evolution, particularly given how impractically large traditional full-size quarter-wave verticals are for many modern applications.
Yeah, so this deep dive really confirms that for these kinds of low power, long wavelength applications, 27 megahertz being a prime example, developing minute control over the magnetic environment around the antenna might just be the modern key. The key to overcoming both the regulatory power limits and the physical space restrictions we face.
It definitely shifts the design paradigm, doesn't it?
Mm.
Moving away from focusing only on sheer physical size and conductive properties towards incorporating precise material engineering and field manipulation.
Yeah.
Which leaves us with a really interesting, provocative thought for you, our listeners, to consider. We established that miniaturization, making effective antennas smaller, is perhaps the greatest promise of this research direction, like outlines. So the question is, how might these advanced magnetic materials, the ones that could potentially create a virtually large antenna in a small physical package, how might they truly revolutionize antenna design in vehicles where space is always tight? Or perhaps even more dramatically, could they finally make truly effective yet compact handheld CB devices a reality? Devices where physical size is currently the most severe restriction. Could this push the boundaries of reliable local communication far beyond what we currently think is possible with just 4 watts from a handheld?
It's an exciting prospect. Of course, further experimental validation is needed, especially testing these concepts in the complex, high EMI environments found inside modern vehicles. But the theoretical potential, as outlined in Lake's work, is clearly defined. It points towards a future where magnetic engineering plays a much bigger role in antenna design. Thank you for joining us on this deep dive into magnetic radio enhancement.
We'll catch you next time for another deep dive into the sources that matter.